So far we have designed all the components for a static analysis based on the abstract interpretation framework. Okay, so from now on, let's see how to implement the static analysis. So static analysis implementation is actually all about computing fixed point. So here, let me introduce a naive fixed point computation algorithm first. Suppose your abstract domain has finite height. Okay, then the algorithm looks like this. Here two variables x and r. Okay, they are elements in the abstract domain, and here the abstract semantic function. In our case, they are these variables. Okay, are actually mappings from labels to abstract memories, right? Okay, then let's get started. This algorithm starts from the bottom, okay, assigning bottom to this variable x, and starts this loop. Okay. In the loop, it saves the old result, okay, from the previous iteration to this variable r, and compute a new result by applying the abstract semantic function. Okay, and then what is this? We check if it is a fixed point or not. Okay, if the newly computed outcome is less than or equal to the old one, it returns the old one. Okay, very simple. But what if the domain has infinite height? Okay, then we can simply extend the old algorithm to use widening here. Okay, here is the only difference, to compute the new x with widening, and all the other parts are the same as before. Okay, let's take a look at the algorithm more closely. Here I inlined all the definitions of the abstract domains and the abstract semantic function with what we defined. Here, this one actually represents the abstract semantic function f sharp, right? Then how to implement this f sharp? Okay, it actually consists of three parts. First, for each label, we apply the abstract transition, right? For each label, we apply the abstract transition. Then we will get a set of newly reachable abstract states, right? And then next, for each label, we partition the resulting abstract states, right? And then the outcome will be a set of abstract memories for each label. Okay, that is the second step. And next, finally, we will join all collected abstract memories and make a single abstract memory per label. That is the last step. Okay. Okay, then let's take a look at this example. There are 4 labels. Okay. Then let's compute the abstract memory for each label using the naive fixed point computation algorithm. So it starts with the bottom element of the abstract domain that maps all the labels to the bottom memories. Okay. After one iteration, the memory at label 1 will be updated like this. Okay, because of this assignment, right? And after another iteration, the memory will be propagated into the loop, okay, because this value is less than 10, which is the condition. Okay, in the next iteration, at the loop head, widening will be applied, which means that here the old value is 0 to 0 from the previous iteration, this one, right? And the new value is 0 to 1. Why is that? Because the join of 0 to 0 from label 1, join of 0 to 0, here 0 to 0, okay, and here 1 to 1, the join of join, okay. So the outcome, the new value is 0 to 1, okay, at label 1. And then according to the definition of our widening operator, the upper bound will become plus infinity because the upper bound is increasing now, okay. And then in the next iteration, the memories at label 2 and 3 will be updated as follows. Here the abstract filter will be applied. So the abstract value of x inside of the loop will become 0 to 9. Okay, according to the definition of our abstract filter, right, the new value for the abstract filter is computed as a meet of the input value, which is 0 to infinity, okay, and the greatest value that satisfies the loop condition. Okay, in this case, this one is loop condition, so this minus infinity to 9 is the greatest value that satisfies the loop condition. Okay, then what is the meet of these two values? Okay, 0 to infinity. Okay, that is the value of x inside of the loop after filtering. And then what about the fourth branch? So the abstract memory at label 3 will be updated to 0 to infinity because of the same principle, right? This is the result of, again, result of the meet operator. The first operand is the input value of x, which is the same as before, and the second operand, right, is the greatest value that satisfies the condition for the first branch, right, which is greater than or equal to 10 for the first branch. Okay, so the filtered outcome is 10 to infinity as a result of this meet operator. Okay, then finally after one more iteration, nothing will change. So the fixed point is reached. Okay. So far so good, but you may wonder the followings here. First question, maybe, why do we have very imprecise result at label 3? The ideal result will be 10 to 10, you may think. And why not 10 to 10 from our analysis? That's the first question. Next one, you can notice that this naive algorithm is very inefficient, right? Every time, each iteration, it will iterate the number of labels, right? Every time this algorithm iterates number of labels. Okay, if the target program is very large, that contains millions or billions of labels, and what happens? It would be very inefficient. Okay. The answer to the first question is actually narrowing. So let's apply narrowing to the result. So the same iteration algorithm will be performed, but with narrowing, not widening. So we start from the widening result. Okay. And after we apply the semantic function once, then what are the new abstract memory at label 1? Okay, it will be 0 to 10. Why is that? Because again here 0 to 0 came from label 0, and because here the abstract value is 0 to 9 at label 2, and then after abstract transition, what is the output? 1 to 10. Okay, and then if we partition this set of memories, and then what happened? The join is 0 to 10. The join of 0 to 0 and 1 to 10 is 0 to 10. That is the new abstract memory. Okay, this one. What is the old one? This is the old abstract value from the previous iteration. Okay, then we apply narrowing for these two abstract values. Okay, what is the result? According to the definition of our narrowing operator, so the result becomes this one, 0 to 10, because the old upper bound was infinity and new upper bound is a finite number. Then we take the finite number. That is our definition, right? So after applying narrowing, the outcome will be 0 to 10 here. Okay. Then the output with narrowing will be propagated to label 3. Okay, here. And another narrowing will be applied. So this new value will be computed after narrowing. Then finally the fixed point is reached. Okay, we will have the result, okay, as we expected. The answer to the second question is the Worklist algorithm. So for each iteration, right, instead of computing abstract memories for all labels, the new algorithm computes only necessary work, and work is maintained by a worklist. Okay, and what does work mean here? Work is a label whose abstract transition should be recomputed. Okay, then why is that? Why recompute? Okay, because each input is updated, right? In summary, we will compute abstract transitions for labels only if their inputs are updated, right? Otherwise, no need for new transitions. Okay, does that make sense? And let's see the all steps for the widening phase. Okay, initially every label is a new work because initially we have to compute all of them, right? At the next iteration, okay, what label should be computed? Okay, the next iteration, okay, because only the input memory of label 1 is updated, right? If you compare these two, if you compare these two memories before and after iteration, and what is the difference? Okay, the only input memory for label 1 is changed, right? That means only label 1 should be recomputed. Okay, and then we have the result at iteration 2 here. Okay, then what is the next work? Okay, let's compare these two. Okay, here the next work is this guy, right? The output of label 1 will affect to the input of label 2 here, right? So label 2 is the new work. Okay, we will safely skip all the other labels. Okay, then in the next iteration, label 1 is a new work because each input is updated, right? So the analysis computes the abstract transition for label 1. Okay, and then in the next iteration, what are updated? Now label 2 and label 3, they are new work. Okay, and then after computing a new transitions from label 2 and 3, okay, then finally there's no more work. That means the fixed point is reached. Okay. So now we have the final algorithms. So the first phase of your analyzer is the worklist algorithm with widening. Okay. This algorithm will maintain a set of work here as a worklist. So initially the worklist contains all the labels, okay, and then this algorithm applies the semantic function f only to the labels in the worklist. Okay, this bar means modulo worklist. Okay, and then construct a new worklist by collecting the labels whose input memory, okay, becomes larger than before, right? And then the iteration will terminate if the worklist is empty, okay, otherwise it repeats. Make sense? Then after computing the abstract element using the worklist algorithm with widening, the second phase of your analyzer is the worklist algorithm with narrowing. Okay. Again, we will maintain the set of work like this, which is the same as before, which contains initially the whole set of labels. Okay. And the whole algorithm is same as before with the widening case. But the only difference is that first we use narrowing instead of widening. Okay. And second, we add new work here, right? We add new work if the input memory of label becomes strictly smaller than before. Okay, because this worklist algorithm with narrowing will compute a decreasing chain. Okay, then repeat this whole step until we consume all the work. Okay. So, okay, let me summarize. So far, we have defined an end-to-end static analysis from the concrete semantics to the abstract semantics. And we have learned how to implement the analysis. Okay. So as you can see, a large part of the design, definition, and proofs are compositional. So you can define and prove the whole structure using those of substructures. Okay. Also, we have learned an efficient algorithm to compute the fixed point, which is called worklist algorithm. And as you can imagine, in practice, there are many design choices for precise and scalable static analysis. And how to design, for example, how to design a partitioning function, or how to design relational abstraction, and how to design abstract operators like widening, narrowing, filtering, and so on. So it will require a lot of knowledge and experience of static analysis. Okay, that's the end of this lecture.